Okay, we're going to move on now with the rest of this pack, and I'm looking at the next sheet which says use Snell's law to solve this problem here. So I'm going to run through this problem. This is a fairly simple problem asking us basically to use the equations given in the data booklet effectively. So we have a prism made of the same glass as above. So on the previous page it asked us, it referred to the glass at the top of the page, and we had to work out the refractive index. That's the example given here, I think. So we're going to use that, doesn't really matter. So we have this certain type of glass and the refractive index is 1.36. So let's write that in here. So we put in here n equals 1.36. So let's now solve the problem. So we're basically using Snell's law, and Snell's law has adaptations as I explained when we looked at the formula book. But essentially we've got the refractive index, we're going to need to complete the diagram, so we need some angles. So we're going to use basically the sine ratio of sine is the ratio of refractive indices. Let's just do that. So first of all let's put a normal line on the incident ray where it strikes the medium, accurately as we can. I'm going to put a normal line using the protractor here. That's the normal line. Let's work out the angle of incidence. I'm going to do that. You need to be really careful, use the protractor correctly. Sometimes the kind of 0 point is within the material of the protractor, but this one starts on the base. You can see that because you start reading the angle from here. So that's 0, 10, 20, 30, 40. And what have I got for the angle here? Let's check that again one more time. Doesn't agree with what I had previously. So I've got the angle between the normal and the incident, 10, 20, 30, 40. It's very close to 45 degrees. Let's put it in at 45 degrees. Okay, now this is really important we get the Snell's law correct, because if you look carefully at Snell's law, the equations, and what I spoke to you before about the slight catch about the fact that the refractive index ratios actually flip. Look carefully here. This is Snell's law, that the ratio of the speeds is the same as the ratio of the sines of the angles. When we look at incident and refracted, we have there θ2 over θ1. Well, sine of θ2 over sine of θ1 is v2 over v1, which is lambda2 over lambda1, but the n values are flipped. This is because we're actually, when I explained before, that's because the n is large, meaning that the light travels slow for the medium. So it's kind of a reciprocal relationship. So it's really important we get, we realise that when we're using refractive indexes, we reverse the ratio, and we just use the formula here. Incidentally, it doesn't really matter whether you take one to be incident or one to be refracted, as long as you stick with the same numbering system, as I hope the example will show. So we're going to basically start with a formula, and the formula is, I'm going to write it up here. So I've got sine of θ1 divided by sine of θ2 is n2 over n1. Now I'm trying to figure out sine of, if I call this kind of 1, 2 here, so in other words to the left of the refraction surface I'm going to call it 1, and to the right I'm going to call it 2, then I want to find θ2. So I'm going to actually flip that formula, which is completely fine to do. So I'm going to start over here with sine of θ2, which is what I want for the right hand side of the boundary, over sine of θ1, which is actually sine of 45 degrees. And that's going to be, so I've got sine of θ2 divided by sine of θ1, that's going to be, don't forget, n1 over n2. And n1, the medium 1 is air, which is 1, and the medium 2, which is the perspex, is 1.36. If I rearrange that and solve for θ2, well, I get sine of θ2 is going to be sine of 45 divided by 1.36, which tells me that θ2 is sine minus 1 of sine 45 over 1.36. And that will give me, if I do it on the calculator, make sure I'm in radians, second sine minus 1 sine 45, divide by 1.36, gives me 31.3. Do a double check here in case you reverse something by accident, and we think about it with our wavefront comes in. Is it going to slow down or speed up? It's going to slow down because the first medium is air, so it's going to slow down. The pen is going to get held back as it enters the medium. It's going to bend towards the normal, therefore the angle will be less. So that's a check. So I can now put in the 31.3, and I'm going to do that by measuring 31.3 degrees off of the normal on the refracted side of the boundary. So 31.3 approximately 31 degrees. 10, 20, 31, put a dot there. And I'm going to draw through, not as far as the dot, but as far as the new second boundary. So that angle there is approximately 31 degrees, the refracted angle. So I'm going to finish this off and work out what happens at the second refraction point or refraction surface. Then I'm going to finish my construction. So now I'm going to use the Snell's law equation again. This time though, I want to figure out the angle that it emerges. I'm going to put just a line on here, a normal line, so that I can draw on the next bit. So I'm going to draw the emergent angle. So now I'm going to call the medium of the prism medium 1, the left of the refraction point, the refraction surface, and I'm going to call the air medium 2. And so now I need to find again sine theta 2, and this is going to be sine of the angle here. We can measure the angle here, the incident angle. Okay, I need to extend that line back so I can read it on the protractor. So I'm measuring the angle between the normal and the new incident, which was the old refracted. So I line that up carefully, and I get 10, 20, almost exactly 25 degrees there. You can tell it's a little bit less than 31, it's not quite an isosceles triangle. So that angle there, what did I say, 25 degrees I think. Let's just double check that. 10, 20, yeah, 24, 25 degrees. 25 degrees. So I've got now sine of theta 2 in this region over sine of 25 here is going to be, I'm going to flip that, so that's theta 2 that has to be n1 divided by n2. So my n1 here, we're referring to medium 1 as being the prism, that's 1.36, and now the medium 2 is air. Again, I solve for theta 2, and that's going to be sine minus 1 of, so if I think about this and this, if I take this 1.36 multiplied by sine 25, I've got sine of theta 2. So therefore theta 2 is sine minus 1 of 1.36 sine 25. If I do that, second sine minus 1 of 1.36 sine 25, I get an answer of 35 pretty much degrees. And I can now draw that in and we're done. I'm going to now draw in an angle of 35 degrees refracted, which makes sense as well because the angle of refraction now is bigger than the angle of incidence because the light speeds up as it passes through this boundary. So I'm going to measure off 10, 20, 35. I'm just going to bend down that way. Okay, I haven't drawn it perfect on the diagram, but it's not bad. And so some of you may have tried shining light through the prism here the other day, and you notice you get a bit of a rainbow effect, and that's because in fact you have slightly different refractive indices for different colours of light, so the colours split slightly different amounts, but that is beyond what we're actually looking at today. So I'm going to move on now to the next page, and I've sort of started preparing for this. And so we're going to use Snell's law to complete this diagram. So let's think about what we got. We've got the ray coming in here, that's our incident ray, and it's going to have wavefronts that we will construct. And we're entering a medium, a second medium. This is air, so therefore n equals 1. This is the medium, and it tells us the refractive index of this medium is, and that tells us then, just quickly reviewing what we did before, that light will travel 1.5 times faster in air compared with the medium. Okay, let's now work through this problem. So we're going to measure the angle of incidence. I've already measured it, it's this angle here. Hopefully you'll agree that the angle there is 53 degrees, or pretty close. So that's 53 degrees. Just going to check the camera switched on. And it is. That's good news. Okay, so that's 53 degrees, and I've got to work out the angle of refraction. And I've drawn it on, you hadn't got it drawn on, so you can't draw it on. We need to work out the angle there. I just labelled it to save time in the video. So we're going to work out the angle of refraction. I'm going to use Snell's law. So if we take this to be 1, this to be 2, I can use Snell's law, and I want the theta 2 to be on the top. It's just easy to rearrange. This little box here I've created at the bottom to allow some space for working. So I'm going to say sine theta 2 over sine theta 1, which is 53 degrees. And that's going to be n1 over n2, because I'm flipping the 2 for the 1 there. Okay, and n1 is 1 and n2 is 1.5. So that implies that theta 2 is sine minus 1 of sine 53 divided by 1.5, which gives me, if you do it on your calculator, 32 degrees. So I can put in the angle of refraction is 32 degrees, I can measure that, and I can put the refracted ray in. Okay, now let's look at wavelengths. Wavelength in medium 2 has not been given, but wavelength in medium in the air has been. So I'm going to work this out, then we'll start constructing the diagram. So what I could do now is I could use, instead of the ratio of the sines of the angles, remember I said earlier on this, let's just quickly review this, that you can extend Snell's law. Sine theta 2 over sine theta 1 is v2 over v1. I'm just going to write this in here. Basically, you might be asked to derive this somewhere, like prove that the ratio of speeds is the same as the ratio of wavelengths for refraction. So if you think about it, v is f lambda, v2 is f2 lambda 2, v1 is f1 lambda 1, v2 over v1 is f2 lambda 2 over f1 lambda 1, but f1 equals f2. Why is that? Because in refraction, as we specified earlier, the frequency is the same in both mediums because the waves can't go anywhere, they have to keep moving forward. So we end up with, instead of v2 over v1, lambda 2 over lambda 1. I just put that in because I wanted to use that here. So I want to find the wavelength in medium 2. I'm going to write down lambda 2 over lambda 1, and I've got to flip the refractive indices. Oops, that should say 1 over, because it has to be reciprocal of this. Okay, that would imply then that lambda 2 is going to be lambda 1, which is 3 centimeters, times n1 over n2, which is 1 over 1.5. 3 divided by 1.5 is 2. Don't forget we're working in centimetres here. So my wavelength of medium 2 is 2 centimetres. Just going to put that in because speed in air we know is 3.0 times 10 to the 8 metres per second. We might as well do this next one while we're here actually. The speed in medium 2, well I can just say V2 over V1 is lambda 2 over lambda 1. So therefore V2 in medium 2 is going to be V1, which is 3.0 times 10 to the 8 times lambda 2, which is 2 centimetres divided by lambda 1, which is 3 centimetres. 2/3 of 3 times 10 to the 8 is 2 times 10 to the 8 metres per second. So that's going to be 2.0 times 10 to the 8 metres per second. And we could have worked that out using different methods. There's lots of methods now using this, like Snell's law has 2 or 3 equal signs, so at this point we can work out that using the ratio of the wavelength or using the ratio of the sine to the angles and so on. Now the frequency in air, to do this last couple and then we'll finish the diagram off, we're going to need the wave equation. So V equals F lambda implies F, okay, F air is going to be V air divided by lambda air. V air is 3.0 times 10 to the 8. Lambda air is 3 centimetres, which is 3.0 times 10 to the minus 2 metres. I want to work out frequency, which is an SI figure, as opposed before I just used the ratios of wavelength, so I could use the centimetres. If I do 3 times 10 to the 8 divided by 3 times 10 to the minus 2, the 3's are going to cancel to give me 1. 10 to the 8 divided by 10 to the minus 2 is 10 to the 8, take away minus 2, which is 10 to the 10 hertz. So the frequency in air is 1.0 times 10 to the power 10 hertz. And finally, the frequency in medium 2, the frequency in the medium is going to be the V in the medium divided by lambda in the medium, which is 2.0 times 10 to the 8 divided by lambda in the medium, which is 2.0 times 10 to the minus 2 meters, 2 centimeters, which gives me the same answer. And I could have just said that straight away because, of course, frequency doesn't change. The speed slows down, the wavelength gets less. The rate of wave fronts moving through is constant, has to be, because anything entering has to leave. So I end up here with 1.0 times 10 to the 10 hertz. Now the most important bit of this whole thing really is constructing the wave fronts. So we're going to put the information on and complete the wavefront diagram. And this comes up quite often in exams. The best thing is to start from the boundary and have a wavefront which actually hits at the normal line. What I'm going to do now is say, okay, the wavelength in air is 3, so I'm going to take my ruler, I'm going to mark off 3, 6, 9 centimetres. I've already got my refracted ray drawn in here, and I know the wavelength for medium 2 is 2 centimetres, so I'm going to mark off 2, 4, 6, 8, etc. Now I'm going to use my protractor, or if I'm pretty good at judging angles, just a ruler, and I'm going to start at the normal. I'm going to draw a wavefront which is perpendicular to the ray in air. And then I'll draw the second one, which is 3 centimetres away, parallel to the first at 90 degrees to the to the ray. And I only extend it as far as the medium because something happens at the medium where the wavefront bends. I'll do the third one as well and carry on. A lot of people only draw short wavefronts, but I like to draw them right up to the boundary, the interface here. And further, you could even put more in here. If I add on a couple of more distances, so that's another 3 centimetres, there's another 3 about there, and I draw my parallel wavefronts. This protractor is quite handy, it has parallel lines already set on it. Put that one in, seems to be about right there. So there's our wavefronts. We can label on the lambda. Lambda equals 3 centimetres. Okay, so what happens now though is we're going to draw the wave fronts continuing through, but now they're going to bunch up, and it's very precise the way this happens because I can rotate this around, and I'm going to start again from the normal. I'm going to carry that wave front on, but it has to bend so that it is still 90 degrees to the new ray, and I'll draw that through like that. And I carry on, and I should find that those markers you don't even need, because it should correspond, the 2 centimeters should make all of the wave fronts continue through if you've drawn it accurately, which it does pretty well. You can even put this one up here on. That looks pretty neat there. We can see a really accurate construction. I can carry on down here. If you really wanted to go clever, you could carry on either side and work out what happens at the edges. I'm not going to bother with that right now. What will happen here though is the light will now re-emerge, and in accordance with the Snell's law equation, that's 32 degrees, that's 32 degrees, it will emerge at 53 parallel, because this side is parallel to this side. The ray that comes into the block will be parallel to the ray that comes out, and that's just using Snell's law twice. I'm not going to do that now. If you want to do it, you can, but I can now just put on here. So the amount of speeding up, the increase in the angle corresponded to the decrease over here. That angle will now be 53 degrees. Okay, I'm going to pause that video and do the last one in just a couple of minutes. Thank you.